cliquear, porque si no, no te va a funcionar el pasador del dispositivo.
Can we start?
Yeah.
Okay, good morning, everybody. Welcome for this new IAA seminar from the Instituto de Astrofísica de Andalucía here in Granada, in Spain. And today we will have the talk by Dr. Mireia Nievas Rosillo from the Instituto de Astrofísica de Canarias. And she will talk about the unrevealing the gamma-ray emission in radio-galaxies and their host. I will give the word to Jorge that he will introduce properly Mireia. So please, Jorge.
Thank you, Rene, and welcome everyone to this seminar. I'm very happy to present our speaker of today, Mireia Nievas. She's visiting us this week from the IDC, from the Canary Islands, where she works as a postdoc on the astroparticle group within the MAGIC and LST collaborations and CTAO. Before that, Mireia completed her PhD at the Universidad Complutense de Madrid, and after she did her first postdoc stage in Germany, in DESI, working the Veritas collaboration, and yeah, now she's working at the IDC in Tenerife. She is focused on gamma-ray emission from active galactic nuclei, blazars, and radio-galaxies, and today she's going to talk us about her work on unraveling the gamma-ray emission in radio-galaxies and their jets. So without further delay, I'll give the floor to her, and I hope you enjoy the session.
Is it recording now? Because I didn't see anything. Okay, so I'm gonna talk a little bit about strategies that we have to try to localize the particle acceleration zones in these sources in active galactic nuclei, and trying also to localize where gamma-ray emission is generated in some of these sources, no? And in order to start with this, okay, it's not working. Sorry. So in order to check, now it's working. Yeah, now it's working. So in order to start with this presentation, just to give an overview of what AGNs are, these are the central parts of a type of galaxy, which is known as active galaxies, which present a significant amount of emission that is not due to stars, to normal stars or nebula or things like that, but it is coming from really the center of these objects, no? And some structures that in some cases that we know as jets, no? This is some examples of AGNs from Markarian 421. This is a BLAC, Centaurus A, this is a radio-galaxy, another radio-galaxy here, another one, and finally one source that has no significant jets, but it is a safer galaxy, but it is also an AGN. Also, you see here that the central part is really bright. So these sources have been in our minds for already quite a while, since the very beginning of the 20th century, in which the first extragalactic objects were discovered, this spiral nebula that later were identified as sources that were outside our galaxy, to the discovery of the first nuclear emission from some of these objects, this nuclear emission from spiral nebula. Some of these objects were very bright in their cores, were not like normal galaxies, to the born of the radio astronomy that really revolutionized the field. So we started to populate catalogs with sources that were intrinsically very bright in radio. And particularly when you combine this with these optical observations of some of these core regions, you really try to, you start to understand what is going on with these sources. No? But finally, the final push on understanding these sources started already in the late 20th century with the first unification models of AGNs. No? Basically, people started to put together all the observational properties that we started to collect from radio astronomy, also from optical, with the observation of some quasi-stellar objects, also with the start of observations in other bands, such as X-rays, gamma rays, etc. So people started to put all together all these pieces and started to create models to classify these AGNs and to try to understand their properties in terms of fundamental properties. There are many ways to classify these sources. I'm not going to enter into this whole mess because I mean, you can classify them, subdivide them in groups depending on different properties. For instance, if the black hole is supposed to be rapidly spinning, or if it is not, if they have optical lines in their spectrum, or if they don't have them, if those lines are broad or narrow, if the jet is very powerful, so you generate these giant lobes, or if they don't have jets, or they have weak jets, and also if they are present in very rich environments, for instance, in galaxy clusters, or they are found isolated or in small groups. No? And you can generate different subgroups depending on all these properties. What we think that is powering these false structures is basically a supermassive black hole in the center, surrounded by a accretion disk. Then we might have some additional structures, such as a dusty torus, that doesn't seem to be continuous, so it is kind of clumpy, etc. In some cases, we have jets. In some other cases, we have some regions that are composed by gas that is either rapidly spinning or rapidly moving and generate these broad lines, or it is more slowly spinning or moving around. So the Doppler broadening is not that strong, and they generate much narrower lines. So we might have many different components in this structure, no? And if we look at different of these properties, for instance, the power of the radio emission, or if there's gamma ray emission there, if the lines are narrow or wide, or if there is X-ray emission, we can come to some of these types of sources. So this is kind of one of the last iterations of one of these unification models. You can have this. You can have a look at this work by Jessica Thorne in 2022, and this is kind of one of the latest pictures of unification models. No. So now, starting from one of the biggest groups that we can look at, which are the sources that don't have jets or don't have significant jets. This has been traditionally identified with sources that are radio-wide. But now we have sources that don't have significant jets, but they have radio emission in their cores, which are the Fano-Rayleigh zero sources. So this is started to become a bit messy, no? Even this big classification. Anyway, the structure is as I explained before. So you have the supermassive black hole, the accretion disk, all these gas structures here, and then you have the infrared source. No, if we look at the sources from this direction through the torus, then this torus will block all the radiation that is produced here, and this is where all these gas clouds that are moving very fast are producing these broad lines. So these sources will kind of hide these broad lines, and we will only see in optical those gas components that are more slowly moving around. So we will only see these narrow lines. If we look more through the jet, we will be able, in these cases, to see these broad lines. No. For jetted sources, the situation is slightly different, because in many of these sources, the emission from the jet is so bright that it hides these lines. But we still have this division made by the orientation of the AGN structure with respect to the line of sight. No? So if we looked kind of through the plane or at high inclination with respect to the jet, what we will see is typically a radio-galaxy, no? One of these sources with giant lobes or some significant jets. Then if we looked at intermediate angles, we will see some intermediate properties between those from radio-galaxies and those from pure blazars. And finally, if we looked almost through the jet, what we will see is basically the jet emission really amplified by Doppler boosting. This Doppler boosting is so significant that in many of these sources, when we, for instance, compare these jetted sources with the radio-wide AGNs in these later sources, what we will see is all the thermal components from the dusty torus. We can see the disk, the accretion disk. We can see some X-ray components such as hot corona, etc. But in jetted sources, this becomes subdominant with respect to the jet emission in many cases. And sometimes all we see is just a component that is signing from basically radio to the optical X-ray band, which we understand as synchrotron emission from some population of electrons that are living in the jet, and then a higher energy component that we are still not sure what is the nature of this one. It could be inverse contour scattering from the electrons that are also producing the synchrotron with some optical radiation field that could be the same synchrotron emission or some external field, for instance, from the dusty torus or from the broadline region, or also some hadronic emission components can also generate this, can also explain this high energy emission. No? For instance, proton synchrotron interactions of protons with matter, with yeah. So this is kind of the Doppler boosting, an artistic view of what happens with Doppler boosting. So if we look at radio galaxies, we are looking at inclination angles that are very large, and the Doppler boosting is not that important, no, for us. This makes these sources only visible for gamma ray instruments if they are close by, because we don't have that amplification to help us to see the sources. However, if we looked at blazars, you have this huge lighthouse effect in which the source, the jet, is really pointing towards you. So this jet emission becomes so dominant that you can see the sources up to perhaps of about 1 or even more in gamma rays. I already said it, but AGNs are one of the most abundant gamma ray sources. In fact, if you looked at the most successful instrument in this band, which is probably Fermilab, you looked at the catalog of sources that Fermilab has observed, probably more than half of these 5,000, 6,000 sources that gamma ray has seen are AGNs. No, this is the last iteration. This Fermilab is a per production instrument that has been working already for 14 years, and it is covering this energy range from around 50 MeVs to around 1 TeV. No? It has many good properties that make it an excellent instrument to study AGNs. In particular, it is working in survey mode, so it is sweeping all the sky in just about 3 hours. So we can do things such as surveys that don't have holes in the sky, so we can study the entire sky. We can check the variability if the sources are bright enough, because it is continuously observing the entire sky. And we can also try to study giant structures. For instance, in our own galaxy, there seem to be some possible remnant of past AGN activity. It's not very clear the nature, but it's known as the Fermi bubbles. But it resembles somehow the giant lobes of a radio galaxy. So we can do the like extended studies. It has a problem, however, because the spectrum of most of the sources, when you looked at the gamma ray band, it drops almost like a power law with some breaks and some discontinuities, but it really drops a lot with energy. No, so when you looked at energies above, let's say, 100 GeVs or 1 TeV, the density of these photons that you collect from Fermilab, it is so low that you will need to integrate a very long time. No, typically around 1 year, even 10 years, if you look at very extreme energies. No, so this instrument is not good enough, no, to do this study. And the solution that people came with was to instead of using an instrument that you launch to a space that is limited by the possibilities of the carriers to these spacecrafts, what you do instead is to use the atmosphere as a giant calorimeter that has a lot of instrumented surface. No, what you will see in these cases will be the development of Cherenkov showers when one of these particles, in this case a gamma ray, hits the atmosphere and starts producing a cascade of secondary particles that they are traveling at higher speed than the speed of light in that medium, and they produce this Cherenkov light. No, and these telescopes, what they have basically is very fast cameras that take these very brief pulses, and they observe something like this. This will be a Cherenkov shower, and by checking the shape of these showers, they can not only identify where the gamma ray is coming from, but also its energy, because higher showers mean higher energy of the particle, and also its nature. No, typically gamma rays are very well shaped as ellipses, but hadronic components, such as, for instance, a proton or a nuclei, they leave quite messy showers in the camera. So we can do all these things with Cherenkov telescopes. These are some examples of instruments that use this imaging Cherenkov technique. We have MAGIC in La Palma, Veritas in Arizona, HES in Namibia, and also LST, which is kind of the new generation of ICTs, the first telescope of this Cherenkov telescope array, also working in La Palma, next to the MAGIC telescopes. Another possibility, but I'm not going to enter a lot in detail, is to use extended arrays of detectors. For instance, LASSO, which is a hybrid that uses different techniques. You have here in the center some giant pools made of water, and you basically study the Cherenkov emission that is produced inside the water instead of the atmosphere, and then some extended arrays of detectors there that cover giant areas of 1 square kilometers. You have HAWK, for instance, in Mexico, which basically has these water tanks. The principle is the same thing. So one of the particles hits produces the Cherenkov, the extended air shower, and then the Cherenkov emission is produced inside the tank. No, these kind of detectors have some advantages in terms of being able to work even if the weather is not good. No, so these ones will need an excellent sky, very transparent, etc. And as soon as you start having clouds and things like that, you can also observe the entire shower. No, but in these ones, you are not that affected by this, so they have a much higher working time. No? But the sensitivity and for instance, the angular resolution or the energy resolution is much poorer. This is the last, probably an updated view of the catalog of very high energy sources that are extragalactic that we have. No, it is available as TEPCAT, and this is a compendium of sources that are, as you can see, they are mainly blazars. This form more than half of the sources that we know. In total, we account for around 100 extragalactic sources. We have some radio-galaxies, so these will be also AGNs, but they are the jet is tilted, and we have other AGNs that might not be very well classified. Some starbursts, these are not AGNs, and some other sources. This is, I think this is updated. GRBs, not these huge explosions in other galaxies. From this list, of particular importance for us will be flat spectrum radio quasars, as we will see, and radio-galaxies. And this is the list, flat spectrum radio quasars, and the list of radio-galaxies that we have seen so far. Yeah, but still the question remains, no? Where are particles accelerated in these AGNs, and where is gamma-ray emission produced, no? So in order to do that, let's start with blazars, for instance. What can we do with blazars? When you observe them, these sources across the electromagnetic spectrum, you see that only in radio you can sometimes resolve the jet in individual features, for instance, and for sources that we can do this, which are sources that are more nearby, we have indeed had some success. No? So sometimes we see these knots in the jet, these discontinuities in the plasma that are evolving over time, so they are moving around. Sometimes they even interact. So this has provided some insights already of what's going on there. Here you have more examples. For instance, also when you change the frequency, you are serving different regions of the jet. Another example, and also another possibility with these sources is to look at their multi-wavelength emission. No? So the idea is basically this. In the case of BLX, what you will have is a source that is almost naked, so it doesn't have this dusty torus, for instance. It doesn't have bright emission lines. So if there is anything, it's only a little bit of gas, no, that is producing some narrow lines, but you don't have these large gas components, no. In these cases, we sometimes see correlation between different bands, the emission in different bands, and this is suggesting that all the emission is coming from a single region. Okay, so you already have some idea that at least you still cannot locate it inside the jet, but you at least know that most of the emission is coming from one region. This is not always the case. Sometimes some of the bands become correlated with others, but there are other bands that are uncorrelated completely. No? So for instance, here you see a lot of activity in very high energies. In X-ray, it seems to be more or less following the very high energy emission, but here in optical, it's basically flat. The polarization is not changing, and in radio, it's basically flat as well. No? So this is probably telling you that the very high energies and X-ray component, they're coming from some region, while the rest of the instruments are following different parts of the jet. No? So this is already interesting, but it is not telling us exactly where the emission is happening. No? The situation is a bit better with flat spectrum radio quasars because we have these additional components, but they are very important, as we will see. So the idea is the following. The very high energy emission happens somewhere inside the jet, but in order for the very high energy photons to escape, they need to be that far away so that they don't have huge interaction with all the optical and infrared light that is producing these components. No? If the region is very close by, the photons field here will be so bright, then there will be a lot of pair production here. So it will really extinguish the very high energy emission. No? And we will only see the lowest energies in Fermi. No? But in very high energies, we won't see anything. If suddenly, for some reason, the emission region moves outside this photon-rich environment, then it will become more transparent in very high energies, so we will start to see some signal. So now we have information that at least either we have an additional component that is being generated here and it's producing our radiation that we see in very high energies, or the component that we had before is kind of traveling or developing in some way, or it is crossing some region that makes it more transparent or in optical. So this is kind of the scenario, no? Here. If you are within this broadline region and within all these fields, the spectrum will be very soft here, while if you are here, you will have a much softer cut, no, in the spectrum. Radio-galaxies give us even more information. In these cases, they are closer, and also the jet is more tilted, so we are not so Doppler dominated, no? Doppler boosting dominated. So we can start to see other structures than the jet. No? In this case, for instance, this is the famous M87, and you start to see all these extended structures. No? So the outer lobes, this kind of halo. You have a cocoon here, you just start zooming in, and then you have the jet. No? And here you can start to resolve it. If you got higher and higher in frequency in radio, you start to go to inner regions until you get to the event horizon. No? This is that famous picture. This is what you see in radio, but it is not only in radio where you can resolve the jet, but also, for instance, in optical, you can see clearly the jet. Even with Hubble that has a very good angular resolution, you can start to see some structures. No? And some of these jets seem to be quite stationary, while others move around. No? And this is the current view of HST. No? For instance, in Hubble, there was this feature, this HST1, that was quite relevant, as we will see in a moment. But also in X-rays, you can even resolve this jet, no? Of this source. In very high energies, the situation is not that great because the PSF is comparable to the size of this outer cocoon, this outer halo. The resolution that we claim in very high energy instruments is typically 5 arcminutes. It would be a bit better with CTA, but still it is comparable with this whole size. No? But what is more interesting of gamma rays is that they trace very well the variability of the sources. No? For instance, we can clearly distinguish where the flares are happening. And flares are telling you that something is going on in the jet, something is changing. No? So if you start to see what caused possibly the flares in 2005, in 2008, in 2010, you start to see the correlations with other bands. For instance, this component, this HST1, this feature, this not stationary knot, suddenly in X-rays, but also in optical, it became very bright. So this is really coming from this region. The core is not very bright here. While in 2008 and 2010, it became again bright in very high energies. When you compare it with, for instance, the HST1 feature, it is quiet here, but the core is suddenly bright. No? And this is also present in other wavelengths, no? Here. So this is telling you that these different flares are coming from different regions. So gamma ray emission can be produced at different parts of the jet of these sources. With EHT now, the situation is really good because we can really go in detail into the jet and really survey the same regions that we think are producing the gamma ray emission, which was not possible in the past. In the past, with lower resolution instruments, we were not always sure if the emission we were seeing was integrating also the external parts of the jet that are not thought to believed to cause the gamma ray emission, or if we were only integrating the interesting part. No? But now with EHT and high resolution interferometers, the situation is much better in that regard. And this is one of the latest works, this EHT multi-wavelength science paper that was published with the 2017 data. Another one is coming from for 2018 data very soon. Now there is a lot of work in the community, for instance, trying to extend these light curves of M87 to also studying not only the flares but also the intermediate and low states. And for instance, one of the nice things that we can see is that there seems to be some transition in the spectrum that we see in very high energies during different states. No, so when the source is becoming a bit brighter, the spectrum seems to change. No, and this is also telling you a little bit of the population of particles that are generating this. No, the electron spectrum and so. Not only M87, we have seen it in very high energies. We have seen other sources. For instance, this 3C264. This is kind of a twin of M87. It has many properties that are similar. For instance, it has stationary nodes, but also moving nodes. But it has also some differences. It is more distant, the source. It is also has a shorter jet. It has less nodes, and the jet inclination seems to be smaller. And in fact, when you looked at the spectrum of this source, it has different properties, right? You notice here that the shape is not the same. No? M87 is kind of low frequency dominated, while 3C264 behaves more like a typical blazar. So perhaps this jet inclination is more relevant than we previously thought in the behavior of these kind of sources. This is a flare that Veritas detected some time ago, and you see here when you compare the images in I think this is probably a radio, or I don't even remember which one it was, or maybe even optical. But in this case, you see here that clearly this region is what is probably causing the outburst. No, this region in the inner parts of the jet. Another field that is quite interesting for us, and we have had a lot of success observing it, is the Perseus cluster. From all these sources that belong to the Perseus cluster, we have only detected two, which are AGC 1275 and IC310. No? These are precisely the two sources that are very bright in radio. So this is a work from one of your colleagues here. But you see here that it is not the only two sources that are detected in this field. We have this guy that unfortunately we have not seen it even with Fermilab yet. Starting with AGC 1275, this is a source that is actually very interesting because it is actually two sources. It is the first one is a radio-galaxy, Alpha Rayleigh 1. So it has a weak or kind of jet that is core-dominated, not weak, but core-dominated. And then another galaxy, which is a typical spiral that seems to be interacting with it. No, so you have all this messy but beautiful picture here. What is interesting about this source is that it had two very bright flares recently. One in 2016-17, detected by MAGIC, for instance, and it became one of the brightest sources in the sky in gamma rays. And another one very recently, just 1 year ago or so, that was detected by multiple instruments, no, and optical facilities, etc. What is interesting about those two events is that they were very long-lasting and they were correlated in many bands, which is not that typical from radio-galaxies in general. So this is what we think about it. So when we study this source, it looks like the jet is kind of preceding. So we have varying angle that we see, depending on where we look at. it seems to have also some gamma ray variability due to some injection of high energy electrons. Yeah, so there are many results when we study this, even some trend that seem to make this source more bright over time, no? Here. In LST, we have detected the source recently. As I said, we covered very nicely this flare in last winter. And we, for instance, see here, this is a light curve. So we are showing the flux emitted by the source at some range of energy, about 100 GeVs over time. No? As you can see, in the first moments, this is just one beam that lasted about 6 minutes. The source was incredibly bright, but then the brightness decreased quite a lot and very fast. No? And this fast evolution can also constrain the emission location in some indirect way. No? So the faster the variability is, the smaller the source, the emission region needs to be because of causality. So in principle, this kind of suggests that the emission region is more closer to the core. No? Well, these are spectra that we have generated just to see that also the spectrum in very high energies evolves over time. So we can see that it becomes suddenly softer. So the kind of electron population becomes has also a softer spectrum than the line population when it is in lower states. No? And this is the sky maps that we have produced for this field. This is the location of NGC 1275. The location of this missing NGC 1265 is here. We have never detected that source in gamma rays. And this will be the location of this other source that we know in very high energies. If you integrate everything, you don't see anything. But if you focus on specific times, you start to see the other source suddenly becoming active. No? So this data set, we were lucky enough to catch the second source, which is IC310. This is an interesting source on its own. This is a source that when you look at it at high resolution radio instruments, you see that it looks like it only has one jet or one-sided jet. But this is actually quite rare, no? For a radio galaxy. You expect always to find in some way the counter jet. And people have started to try to suggest possibilities to explain why we don't have this counter jet, and they become also using information from other bands, such as in gamma rays, in which this source behaves really like a blazar. So it looks like the jet is aligned with the line of sight. For instance, you get this possible explanation in which you have a very strong bending of the jets, and you are looking in the exact position where one of the counter jet is really behind the jet that you see here. IC310 in gamma rays was very important as well because we observed record fast variability in the past. In 2000, I think this was for 13 or 14, the data that we observed. And this source became really bright. So it was 5 times the graph, which is our kind of standard candle in very high energies. And the evolution time, so it was increasing and doubling the flux emitted in just a matter of few minutes. And this is really pointing to a very, very, very compact emission region. And if you start to apply the math to see where it could be located, it seemed to be produced really in the innermost part of the jet, almost in the near the black hole. So people started to interpret this data, for instance, in terms of a magnetosphere instead of a classical jet emission. No? They use, for instance, pulsars as an example, in which you have a magnetosphere. You might have gaps there that are accelerating the particles and producing the gamma ray radiation. So they started to interpret this as something similar. This is, again, what we see in LST. We didn't catch this first flare because, of course, the instrument was still not operating. But we caught this event here that we are still trying to study, no? Put in context of a more broad multi-wavelength emission. And this is the spectrum that we see, just to give you some recent hot results. we have more sources now moving to the southern hemisphere, in which we have another two sources that we have observed. Let's start with the most interesting one, which is Centaurus A. This is a very, very nearby AGN, and this is a giant, really a giant galaxy that as we see it because of this very close distance. No, in radio, it has a very, very complex structure. For instance, you see these giant lobes here, but when you look more to the inner jets, the situation changes completely. No, so at kiloparsec scale, it looks like it is only one-sided, and if you go to parsec scales, so parsec scales, you start to see the jet and counter jet. So the shape is completely changing here. No, so this is again another example of how messy and how complicated jets are. No, that at different scales, the viewing can change completely. In high energies and very high energies, the source is particularly interesting. So this object is huge for Cherenkov telescopes. And in fact, when you study the emission as a function of energy, you notice that at different energies, you are seeing different components. No, so at lower energies, with Fermi, for instance, what you are seeing is basically the emission from the inner part, while at the very high energy seen by Hess, you start to see the emission, the extended emission from the lobes. And this was a really high impact result made by Hess, no, in the past. And you see here the change in the spectrum, these two components. No? So you have here the more close region here, and suddenly the source becomes harder in the spectrum when you look at the extended. And finally, the last source that we have detected in this group is this PKS 0625. Unfortunately, we don't have that many details about this source. It's quite recent discovery, and it is way more complicated. The distance is much higher. Looks like it could be a twin of IC310 in the sense that it has some similar properties. Depending on the energy component, we are looking at a source that behaves as a blazar, so kind of jet oriented toward us, while in other energy bands, it behaves more like a radio-galaxy itself. No, the jet angle is not very well constrained, unfortunately, so we cannot really get into the physics yet, but it has been recently detected, and probably Hess is still observing this source to make better constraints. And with this, I want to close the talk. Unfortunately, I cannot tell you where the emission region is placed in these sources. This is a search that still continues, but I have presented some of the strategies that we are currently using. So basically combining high resolution imaging with variability studies. Thank you very much.
Thank you, Mireia, for the very interesting talk. So we have some time for questions. So if anyone wants to ask something to the speaker.
Very nice talk. Thank you. You said at the beginning that there was like something like 100 very high energy source ever detected. Is that correct?
Extragalactic ones.
Extragalactic one. And then from there you have like 5 or 6, or I don't remember, radio-galaxies.
Yeah.
So that's not a lot. So I guess with the CTA, you're gonna have much more sensitivity, so you're gonna detect much more. So what are the numbers that? What's the future about that, basically?
So one of the possibilities that we are working on is, for instance, suggesting clusters, observing clusters, because these sources are very often found in clusters. So they are not isolated like flat spectrum radio quasars that tend to be in smaller groups, but particularly these radio-galaxies tend to be found in these giant clusters. So looking at those clusters might give you additional sources. But of course, I mean, we don't know enough about the gamma ray emission. In some cases, it seems to be only present in some occasions. In NGC 1275, for instance, it is quite variable, and you often see the source. No, it's quite bright, and it behaves more like a typical blazar in the sense that it has often flares and so on. But other cases, for instance, IC310, you barely see it. You see it only when it flares, which, I mean, you cannot trigger those observations from other instruments very easily, because in other wavelengths, you might not see anything. changing there, M87, for instance, even though it is very close by, it has been silent for already many years. So you basically have some hint of emission there in gamma rays, but it's very weak. Of course, with CTA, you will have a better sensitivity. So these kind of steady sources, you will be able to see a few more, perhaps. Or for instance, M87, you will be able to see the emission in shorter periods of time. But still, I mean, I'm not sure if there is a huge estimation of how many sources we will be able to detect. Also because in the instrument that we use the most to make these predictions is Fermilab, and in Fermilab you don't have even that many sources of this type.
So because of the variability, you never know, so it's really hard to find them.
Yeah, also because you cannot really constrain that well the emission because you don't have Fermi to say like, hey, I detect this source with this spectrum, so if you extrapolate it here, you can make some numbers of whether you will be able to detect it at even higher energies or not.
Yeah.
You don't know how these sources emit in general in the gamma ray band. So you often see them in radio. Sometimes they have powerful X-ray emissions, sometimes they don't. But that's pretty much it. So you don't know how this component evolves with energy. So I think these detections happen typically in a serendipitous way. So you are observing some field and suddenly you see a source and it matches radio-galaxy.
I see.
Yeah.
Thanks, Mireia, for the talk. I have a question regarding IC310 and the new data.
Yes.
So have you considered or have you done any variability studies with these new results, or is the significance of the signal too low in order to be able to confirm what was?
It's around
detected in
8
question?
sigmas or so, 9 sigma, but we barely have 1 hour and a half of data, so it's kind of tricky. I mean, we can check if there was something changing during that hour. The source is well known to develop really fast variability. So often the flares from this source, they last 1 day and it's gone. So this is a possibility indeed, but I'm not still pretty convinced by the signal.
I was wondering whether you could.
I mean, we will
you could be able to detect some flickering as the one that was detected in 2013.
The flare was not as strong. So in the 2013 flare, it was reaching, I think it was 20 times this brightness, something like that. So it was much easier, or even more, or 30 times.
Thanks.
But again, I mean, there was nothing in other bands that really identified this pulse in a sense. So these observations is really important to monitor the existing sources with very high energy instruments, because you have really no other way to trigger these observations. And in cases like this one, that the observation lasts, so the flare lasts just a few hours or 1 day, I mean, you cannot efficiently trigger it from other instruments. You will be basically too late for these sources.
And this one was basically seen because you were looking at 1920.
Yeah, because we were monitoring.
Okay, thanks.
Another question? I actually wanted to ask you about NGC 1275. So yeah, this is quite a peculiar case because it's not just like one source, but this system of two interacting galaxies. Do we know if this nature, these two interactive objects, this interaction plays a role in the emission that we see from dinosaurs?
To be investigated.
Okay. Okay. So any other question here, or maybe in the Zoom? Not, I think we can close the seminar here and thank the speaker again.